Welcome everyone. First thing I would like to introduce Doug Kinsella and myself, Matt Bjorum. Today we're going to strictly focus on the quick capture technology of Core Pro. We're going to discuss the different types of analytical sources of getting and bringing core or rock to surface. Quick capture tool overview, we'll go over the coring configuration approach, also look at drill ahead capabilities for wireline for increased cost savings. Quick capture animation, actually an animation of how the video or how the tool works downhole. The tool assembly, we'll look at the actual breakdown and the components of the tool, look at how the tool is set before it goes into the hole, and also give a tool activation example. Surface handling and data acquisition, once we bring that tool to surface, what we do with the data, what we do with the tool, how do we transfer the liquids, and how do we collect all the gases. And then we'll shortly go into some of the obtainable deliverables and then have a question and answer session at the end of the presentation. First thing we have to look at is, from an analytical lab's perspective, is how do we get a hold of rock at surface to be able to analyze its certain properties. There's several different methods of collecting whole rock samples, whether it be cutting, sidewall, conventional wireline, or pressure coring that we talk about. The importance of what we want to look at is the actual physical material that we collect from core, and also how fast we're able to bring it from downhole up to surface. So if you think of it from a spectrum, you look at drill cuttings. Drill cuttings are a continuous effort as we're in the drilling and coring process. You can collect those. You have very fine, potentially fine-grained material to do analysis on. As we start moving up the spectrum, we can look at sidewall cores, actually going in and taking percussion or rotary sidewall cores. If you think of the surface area of a rotary sidewall or a percussion sidewall core, it's very small. The amount of analysis that you can do on those cores is limited to the actual surface area. We move into larger material, conventional and wireline applications. Conventional applications, you're able to take large core sizes. As we move into wireline coring, that's where the speed and the quickness of how you can get the core to surface comes into play. Wireline core, you're able to take similar diameter cores, bring it to surface in a fast manner. What you have to think about as we move into pressure coring, in the other options between wireline and conventional coring, as we're physically tripping out of the hole, we're losing any of the in situ properties from the core, all of the liquid and all of the gas. Pressure coring or quick capture coring, as we're going to discuss today, takes out any of those variances.
So 2 or 3 years ago, we set out to design a better mousetrap. We know from the last 3 or 4 decades, pressure coring has been in the industry. It's had reliability issues. It's had small diameter core, which in essence, when we got to the lab, had a difficult time to do any type of analysis on it. So we really tried to take a step back and look at how pressure coring worked, what it delivered to the client, and how we could change it to make it more repeatable. One of the things, the main problems, if pressure core worked, it came to surface, and we had to take that core and bleed it down to eventually to an atmospheric pressure. So we bring a core to surface. We had to design a set of tools that were extremely robust, that could handle maybe 10,000 psi of pressure. In doing that, we ended up cutting a small core, inch and a half diameter. So we thought just outside the box a little bit, and we said, if we're going to bleed it down on surface, instead of bleeding it down on surface and bringing this methane-filled bomb, why don't we bleed it down on the way out of the hole? So the whole really idea behind the tool is capture everything in the core, it comes to surface as a reduced pressure and stores everything in the core barrel and canisters. What does that do for us? Well, obviously we get to keep everything that come out of the core, so we get to capture all the expelled gases and fluids. We can cut a much larger diameter core, 3-inch if we're doing a wireline, 3-inch if we're doing it on a conventional platform in small hole, 6 1/8 or greater. Or we can cut a 4-inch diameter core if we're in hole sizes 8.5 and above, and we run it on the conventional coring platform. The tool is designed with a 10-foot barrel. Honestly, it's an arbitrary number. We chose 10 feet for coring efficiencies. Also, we chose 10 feet for a day to pack within a certain amount of reservoir. As the tool has expanded market and expanded reservoirs, we're now understanding there may be reservoirs where we only want a 3-foot barrel. There may be reservoirs where we want a 30-foot barrel. We will be offering the option of the length of the barrel to match the demands of the formation and the answers you're looking for. There's pressures and temperature transducers throughout the barrel and the canisters. This allows us to record what's happening as we're coming out of the hole, and we can watch the barrel vent off the gases expelled from the core and store them in the canisters. We limit the tool to a 500 psi working pressure on surface to create a safer work environment. And as most people like to know, we have a new type of valve. It's a proprietary sealing system on the bottom, and that's what gives us a mid 90% efficiency and repeatability in the tool.
Now we need to discuss the different types of coring configurations and approaches that clients would take, that we would work with you independently, spend the time working over what is your target reservoir, what are you trying to achieve. We have, as I discussed earlier, the different types of methods. Conventional versus wireline method. How do you make that decision? Conventional method, you use the drill string that's already there on location, cost savings for the client yourself, and additionally working with the rig. We can take both a 3-inch and 4-inch applications. Conventionally, you're limited in what type of kit you needed to move to location. There's no extra drill pipe required, but the main importance for this is it's suited for shorter coring intervals or long drill breaks in between coring intervals. If you're only looking at taking, 2 120-foot coring intervals and they're spread out over, 300 meters, 100 meters, 1,000 feet, it makes it makes the case for the conventional application. As we move into the wireline application, the big point that we need to discuss here is there's no tripping required in between coring intervals. If you look at the coring configuration on the left side of the screen, we can easily go from 90-foot coring applications, go straight into a quick capture application, go back and forth as we go down the hole. The other benefit that is capable is drill ahead capabilities. If we have long coring intervals and short drill breaks, we simply insert a drill insert and drill from each coring interval to the next as we travel down the hole. We can run any type of configuration. We work with you, the client, or work with the laboratory themselves to ensure that we get the most efficiency out of the coring configuration approach. As discussed, here's just a quick blow-up of the coring and drilling mode. Simply be able to go from actually coring your rock, dropping an insert in, drilling ahead to the next target coring interval, and then switching back and forth depending on the coring plan. Yeah, here's a quick capture animation. The animation focused directly on the wireline platform for the purpose of the video. You can just imagine it on the conventional application. It has 2 parts to the video, both the coring operation itself, it'll show you a quick core to quick capture operation, and then transfer into the actual surface handling of the barrel and the canisters once they get to surface.
The revolutionary technology behind QuickCapture allows 100% of all in-situ gases and liquids to be collected at safe working pressures, giving a complete and accurate picture of the reservoir to guide productivity while speeding up on-site decision-making and avoiding rig downtime. Traditional pressure coring technology has only been available in conventional coring applications, which means the drill string has to be tripped in and out of the hole to cut and recover the core, which adds significant rig time costs and more safety concerns, as most accidents on a rig floor occur during tripping operations. With the introduction of CorePro's revolutionary technology, QuickCapture, all coring operations can be operated by wireline, and the tool has been developed to run on CorePro's QuickCore wireline platform. The well is conventionally drilled until core point is reached. The drill string is then pulled and the wireline coring tools are tripped in the hole and the inner barrel assembly is pumped into place. Coring of the target section then commences with continuous core runs of 3-inch 76 millimeters up to 120 feet 36 meters in length. Once coring is underway, the core is stored safely and securely in the inner barrel of the coring assembly. Once the barrel is filled, the inner barrel assembly can be extracted from the core barrel via wireline. Once the quick capture coring interval has been identified, the pressure coring assembly is pumped into place using the same wireline platform without having to trip tools out of the hole. The quick capture outer assembly consists of the same swivel assembly, outer barrel, and core bit. The inner assembly consists of gas storage canisters meant to collect any expelled gas or fluids during the trip out of the hole. The telescoping sleeve is used to collect the core. Pressure and temperature transducers are to monitor coring operations and the trip out of the hole. All of the core and associated gases and fluids in the tool are sealed by a valve. Coring then commences collecting up to 10 feet, 3 meters. After the interval is cored, the assembly is hoisted off bottom to break the core at the bit. The wireline is run down and latched onto the quick capture coring assembly. An initial pull begins to set and stroke the tool, allowing the core to pass the valve assembly and seal the tool. A secondary pull disengages the tool, and the inner barrel starts the trip to the surface. As the tool is being tripped to the surface, the decrease in hydrostatic pressure allows the core to release gases and fluids. For safety precautions, the tool is not allowed to reach any pressures above 500 psi, so as the tool is tripping out of the hole, all gases and fluids that are expelled from the core barrel are collected in the series of gas storage canisters on top of the tool. Each canister is fitted with a pressure relief valve, pressure sensor, and pressure and temperature recording transducer. The pressure relief valve works by a pressure differential preset on the tool to allow communication between the barrel and canisters once the desired pressures are met. As another safety precaution, the tool is fitted with pressure dump valves. In case of any failures in the tool due to plugging or malfunction, all of the pressure will be released. Once the tool reaches the surface, it is laid down and the barrel and canister recovery process begins. First, the gas storage canisters shut in and then are removed from the tool and set aside for future analysis. As the core barrel is still a live system, it becomes the first priority of the well site hands. Pressure and temperatures are downloaded to monitor the tool and deem a successful test has been completed. Next, all the gas is released from the tool with the total volumes being measured and recorded. Once the tool is lowered to 0 or an acceptable pressure, the core is extruded and transferred to a transportation canister. The core barrel is then wiped clean, with all fluids collected to be transferred to the lab for further analysis. Lastly, the gas storage canister recovery takes place. Pressure and temperatures are downloaded to monitor the tool, and total gas volumes are measured. Once all of the gas has been measured, the fluids are pumped out of the canister and collected to be sent to the laboratory for further analysis. CorePro, the world's largest coring provider.
So now a little bit of nuts and bolts about how the tool works. We have a simulation here. This is the barrel turned sideways. It's not horizontal coring, it's just turned sideways for ease of showing you how it works. We have a barrel and it's full of core. On top of that barrel, we have pressure and temperature transducers that are monitoring what's happening in the barrel while we trip out of the hole. On top of that barrel is a canister. Canister is a little bit unique. Inside it is a piston. The piston is capable of floating. On one side of the piston it sees reservoir pressure, or not reservoir pressure, it sees hydrostatic fluid column pressure. It's very, very important. This is what's going to monitor the pressure of what's happening inside the system. So on this side of the piston we always see fluid column pressure as we come to the top of the hole, get closer to the surface. The amount of pressure we have, it's just like water getting shallower. Less pressure on the back side of the tool, it's easier for the piston to move. On the way out of the hole, the inside of this barrel wants to maintain downhole pressure. If we're in a wellbore that's say 10,000 feet deep, we have a roughly 5,000 psi as we're sitting on bottom. We cut the core, we activate the tool and close the valve. As we start to come to surface, that pressure on the outside of the barrel is getting less and less and less. We will reach a point where the core wants to evolve and let go of some of its gases or its liquids. When that happens, the volume inside the barrel wants to grow. Gas wants to, it's very small, it wants to get bigger, so it wants to expand in volume. When that happens, we will create a pressure differential inside the barrel. The pressure inside the barrel is going to grow. The pressure on the outside of the barrel is going to decrease because we're getting closer to the surface. The water is getting shallower. When that happens, the pressure relief valve in the top of the tool opens. When it opens, we push liquid and gas up into the canister. This event is repeated over and over and over as we get shallower out of the hole. First we fill one canister, then we fill the next canister, the next subsequent canister after. We have a lot of questions about why a pressure relief valve. Why do we need it? We use a pressure relief valve as a tattletale, as just a way to make sure that the tool is functioning properly. If we left the top of the tool open, the instant it started to evolve gas, it would start to migrate into the canister. But if the valve leaked, it could migrate the other way, and we would never really see. By installing a pressure relief valve, we actually create a pressure inside the chamber. If that pressure on the plots, when we get to surface, was declining, we would know the valve was leaking. So it's a way for us to communicate to the customer that, listen, we know the chamber was sealed. We can see it build to 250 psi greater than the pressure on the outside of the barrel. And then we can see the valve open. Now when the valve at the top opens, the pressure relief valve opens, we can see it dumping into the canister. So it's just a self-check that the tool is working properly. Otherwise we would sit in front of the client with our plots and there would always be some questions. Did the valve leak? This is our way of saying no, and here's how we can prove that it didn't. The tool is set up in the shop in a standard configuration. The reason I use the word standard is because there's not a standard reservoir that we are using the tool in. Reservoirs are different all over the world. We start with a basis. We put a 250 psi relief valve in the top of the tool, a 50 in the top of the next canister, 50 in the top of the next canister, and then we put a 500 on top of the last canister. And this is our fail-safe. This is our parachute. If we ran our calculations wrong, we could get to a point where we filled the whole system with so much gas that we could have a dangerous situation on our hands. So we give everything a place to escape if we ever made a miscalculation or if we hit an incredibly sweet spot in the reservoir that was full of more gas than we anticipated. One of the important things here is this is just a standard setting. If your reservoir calls for something different, if the lab wants to do something different, the entire system is adjustable. We can go from one canister or we could go up to 7 canisters. Average application we find as we're doing this tool around the world is 2 to 3 canisters that we need. There's pressure relief valves all along the way, should the tool plug in any certain port, each one can be vented for safety, and we don't overpressurize anything in the system. There's a little bit of confusion often in the tool, so we put this slide together just to walk through how things happen. We cut the core and we fill the barrel full of core and we close the valve. On the way out of the hole, we're building pressure inside this barrel. When the barrel gets to 250 psi greater than the pressure on the outside of the barrel, the valve opens and we start to fill the first canister. As the canister fills, the piston that I showed you earlier in the slide moves all the way to the end, and it becomes a solid volume that now is going to increase in pressure. When that increase in pressure happens, eventually we have to crack this valve and start to fill the second canister. Pressure relief valves work in an odd way though. They sense the difference in pressure from one side of them to the other. So as you can see, we only needed 250 psi in the barrel to make it open and fill the first canister, but now as we get 50 psi in the first canister, we actually have to have 300 to open. So it's a little bit of a populating effect. As we go to the next canister, you can see the trend of what's happening. So this one now becomes 50 psi, we need 100. Where all this pressure comes from is you have to think about if this event is happening at, say, 3,000 psi coming out of the hole, our volume of gas is still extremely compressed. It's like a balloon on the bottom of the pool is small, but when you bring it to the top of the pool, it's growing 2 or 3 times in volume. So as we're coming out of the hole, we have to do something with that gas that's growing. As we go up through the canisters, each canister needs to increase in pressure as well. So eventually we get down here to 350 psi in the barrel. We've miscalculated, we've hit the best spot in your reservoir that could ever be, and we've got too much gas. The system's designed, there's a pressure relief valve at the top, it's a bit of a panic valve. It's going to open and simply vent into the wellbore on our way out. Yes, we lose some data, but at some point in time, safety is more important than the data. What it would mean is we'd get to surface, we'd have 500 psi in the top canister, 550, 600, and 850 psi in the barrel. You're probably thinking, hang on, 2 or 3 slides ago, you said the barrel was only going to be at 500 psi. These are simply knockdown pressures. The barrel can handle 1,000 psi working pressure. We've had wells where we've increased the pressure to run it at 1,000 psi. This is just really to show you that the tool is safe even if we ever had more gas than we thought we would have, because it's somewhat of an unknown. My favorite part. These are pressure plots. This is what we're going to give you at the end of the well. We cut your core, we start to come out of the hole, and there's a whole series of lines that need to be paid attention to, but we've basically boiled this down to 3 that are important. Red line on the bottom is temperature. Temperature greatly affects pressure. Drop temperature, pressure drops. The reason it's important is because often you could think possibly the valve's leaking, the pressure's going down. But if you look, maybe we've had a 10-degree drop in pressure and 10-degree drop in temperature, and then the pressure just is going away. What this is an example of is we've wirelined a core. We've cut the core, getting ready, wire lines attached, we've activated the tool, and now we're coming out of the hole. Blue line is what's happening inside the core barrel. Pink line is what's happening inside the canister, and until we completely populate that first canister, this pink line represents mud column pressure. Flat spots, so pink line is going down with pressure, bottom is time. That's just simply us tripping out of the hole on a wire line. The flat spots are when we stop in the wellbore and we give the wire line a chance to loosen or untorque. It's just something we have to do with a wire line so it doesn't hurt the wire line. What we do with that time, though, is we use that time to determine if our tool is leaking. So it's another proof positive test for a customer to understand that the tool is not leaking. While the lines are together, it just means that the core hasn't given off any gases at that point. So at some point as we come out of the hole, we're going to reach I guess a less enough degree of pressure on the core. It wants to evolve its gases and liquids out of it. So this isn't happening yet. We sit here, everything is still in static pressure. And then there's a point where we stop and we can see the blue line starts to separate from the pink line. What this is telling us is the core is now starting to evolve liquids and gases off the rock. You can see the pink line is essentially flat. It's just sitting there measuring static pressure in the wellbore. It's at the same spot, but yet the blue line is starting to diverge and build pressure. We continue to trip out of the hole, so you can see the static column pressure declining, but the pressure in the barrel has a mind of its own. Pressure continues to grow, and all of a sudden we're going to hit this magical 250 psi mark where pressure inside the barrel is greater than the pressure outside the barrel. And you can see, oh, there's a pressure decrease in the barrel. What this line is the pressure relief valve opening and pushing fluid and gas into the canister. Now we see it goes flat again. This is something that we've deemed the staircase effect. When it goes flat, that's all the time it takes for the barrel to increase and go the 250 psi differential again. We drop, we build, we drop, we build. These lines, the longer the tread of the stair is how slow the core is evolving gas. If the gas is just slowly leaching out, it takes quite a bit of time to bring the barrel up to 250 psi differential again. If it happens almost immediately, that's a sign of how fast the core is giving off the liquids and the gases. So you can see here as it's just starting, it's taking a little bit of time. The next steps though, it's very rapid. We're building that pressure in the barrel very quickly. The longer vertical lines, that's what we believe to be a sign of whether we're pushing all fluid, all gas, or a mixture. So if you're pushing fluid out of something, if you were to let the air out of your tire, it takes quite a while to take any volume of air out. If you're pushing liquid out, you can advance a small amount of liquid and it decreases the pressure incredibly quickly. So a long line like this would suggest we're pushing a lot of gas out. A very short line like this would show us that we're probably pushing with the gas, we're forcing a bunch of volume of liquid out as well. So it's the duration that pressure relief valve is staying open. We continue. It's a staircase effect or a sawtooth effect. It's just the tool building and dumping as we go. Now we're on surface. Seems like things start to slow down. Are we not building as much gas anymore? This is where we have to pay attention to what's happening to our temperature. This well was done in a very cold environment, and now we're out of the mud column and out into that harsh cold environment. So things start to flatten off, but we're losing pressure, we're losing temperature very quickly. We're going to go into the next portion of this plot. I'm going to have Matt explain it a couple of slides from here.
Where Doug left off, we have the barrel on surface. What happens to it at that point? The first thing that we need to do is download the pressure and temperatures to get an idea of how the core behaved as it tripped out of the hole. Lay the barrel down on surface. We'll simply hook into the gauges that we have. We will download the pressure and temperatures, monitor those gases and liquid evolution, and also monitor the behavior of the barrel. The barrel is still a live system. If it's extremely gassy and it's still building pressure, we want to be able to look at it to ensure that once we transfer it to the laboratory, it's in a safe manner. We start by downloading all the pressure and temperature data, and then we go into the core barrel and recovery process. We're working with all the major laboratories around the world at this point, learning them on the specifics to the tool, working with them to develop different handling procedures and the transfer process. There's there's several points, I guess, to what we do with the data acquisition process. We bring it to the laboratory. Normally the pressure and temperatures are measured and recorded. We take all of the gas out of the barrel at first. We either start by measuring all that gas using empirical methods, getting a hold of the actual gas content numbers in the barrel itself. Portions of those are actually collected for gas composition and isotope measurements to be done by the laboratory at a further point. And then at the end, once the core is extruded, we collect all of the fluids associated with the sample. As Doug showed you the beginning portions as we trip out of the hole, the barrel actually reaches surface and we're able to record the pressure and temperature during the whole acquisition process as well. We have the staircase effect still going on. If you think of the core as a live system, once we bring it to surface, the safest place for that barrel is to be hooked up to the canisters themselves. The activation process that it's doing downhole can be mimicked once it's actually sitting on surface as well. So if it needs to continue to build pressure and relieve pressure into canisters, we physically just let the core do its own expulsion process. Once we bring it to surface, we start to monitor. You'll see several events as we go down. Each one of these events can be recorded and timed to ensure that as the laboratory is working on the barrel itself, how do we timestamp that back to what was actually happening in the barrel? You'll see several pressure decreases. You'll see the barrel actually makes it to surface. We start monitoring the pressure. You'll see pressure increases going on. You can see that it's still activating with the canister down here below. At some point, the core is deemed safe to move it to the laboratory. The laboratory will start out by bleeding all of the gas off, collecting and recording that gas. If we're doing any type of transfers of gas or liquid, we'll see large pressure decreases where you would bring an evacuated cylinder. In the case of this project, bring an evacuated cylinder, hook it up to the barrel itself, open the barrel, evacuate all of the gas, and you get large pressure decreases. As you can see, we did a large pressure decrease right here. The core itself is still an active and live system. It starts to build pressure. At that point, we hook another evacuated bottle to it, do another large pressure decrease, and follow it all the way out. At some point, the core will be lowered to an acceptable pressure, whether it matches hydrostatic pressure. If it's still a live core, it may never, reach an acceptable PSI before you extrude it. A lot of methods would be to actually chill that core, put it to sleep, let the gas evolution process slow, and as soon as you're done with the core barrel, you'll see activations with the barrels themselves, or with the canisters themselves over here. We treat the canister exactly like we do with the barrel. We pull all the gas off of it, and then we pull the liquids off as well. We're able to record the temperature changes as we do. Many applications, you'll actually heat the sample, so we'll be able to help drive off the gas itself. So you'll see temperature changes from the temperature recorders. Core extrusion process. As I discussed, at some point we have to extrude the core from the barrel. That core needs to be transferred to something acceptable to transfer from the well site itself back to the laboratory. There's several different methods that are being used right now. We work with the client, we work with the laboratory specifically to develop how we'll monitor and how we'll actually do that transfer process. The example being shown here is the core is simply extruded from the barrel itself as a 10-foot piece of core directly into a 10-foot adjacent canister. Extrusion processes are very quick for the most part. Giving this method simply is 5 to 10 minutes by the time you open the barrel and transfer it directly over to a canister itself. The first question is, how much is lost during that transfer process? From a gas perspective, is one of the reasons that we monitor the pressure increases over time and then take total volumes. So we can plot volumes and pressures against each other, know how much the core is physically giving off in a 5 to 10 minute period, and apply that back into the total gas calculations. From a fluid perspective, it is extremely important that we collect every drop of fluid. So that process is fairly quick. We'll just use drain and collection buckets. At the time that it's actually transferred into a barrel, the custody of the core itself is handed over to the laboratory. Collecting all that fluid, as I discussed, is extremely important. So we want to ensure that not only is the barrel or the core itself wiped clean, but also we need to get everything out of the barrel. So we've developed a few methods to actually cleaning the inside of the barrel itself, plunging it, actually pushing the liquid through depending on the reservoir type, keeping the barrel heated to ensure that we get everything clean. Everything's collected into some type of collection. All of it's labeled, measured, weighed there on location, and then transferred to the laboratory for fluid analysis. Canister recovery is almost no different than the barrel itself. We originally set the canisters aside. Canisters are then transferred back to the laboratory. Once it's deemed that all the gases and liquids will be pulled off. As you would have seen in the video, you can see how the piston both builds or moves as it builds pressure. We pump into the backside of that same exact piston as we go to extrude the liquids at the end of the project. Same thing, we monitor all the pressure and temperature data. We collect all the total volumes of gas, all the total volumes of liquid, and then transfer all that to the laboratory. Next we'll go into just a quick overview on the obtainable deliverables of the tool itself. As the tool is being put out into the marketplace, there's several applications for the actual deliverables from what the tool itself can do in different types of reservoirs. Are we in a dry gas? Are we in a wet gas? Are we in a liquid-rich environment? Obtaining all that information and working with the clients is the most important thing. So we can help design and develop the tool, the coring configuration approaches to reach these certain types of deliverables. Some of the deliverables that we are putting on the tool at this point, getting a hold of oil in places, getting a hold of gas in place, looking at gas to oil and even water ratios, looking at gas content analysis, looking at oil and gas compositions, looking at the geochemistry from both the gas, the rock, and the liquid itself, and then all types of reservoir fluid analysis, trying to tie that back to saturation measurements, looking out there into any types of PVT analysis that we can adapt to the tool. I've placed the etc. at the bottom as the tool is new to the industry, and we're changing and working in different plays all over the world. We're hoping the list will go on and on and on.
So that's the presentation. Probably just opening the floor now to anybody who has any questions.
I have a couple of questions.
Sure.
So once you get the tool back to surface, you have the core inside the assembly, the quick capture assembly. Is it best to leave it there, or do you transfer that outside of the quick capture canisters?
Yes. The example specifically that we had on up in the graph showed a very short time period from when the core reached surface till we transferred it. In that example specifically, the core was able to evolve gas quickly. We deemed it safe to do the transfer. In other cases that we've found, that duration is a lot longer, upwards of 3 to 4 days, where we bring the tool to surface, we lay it down, the lab keeps monitoring it. The importance is we want to be able to develop a trend of how fast the gas is evolving. So once that transfer process happens, we can predict if the fact that there was potential gas that was lost. If we use a cooling method and physically put the core to sleep, we can actually put a vacuum on the core. So during that 10-minute process, we know specifically that the core didn't move anything or lose any gas from the time that it was extruded from the barrel and placed into a canister itself. So we use the gas evolution trend versus time trend.
So you're answering my other question of how much gas evolves as you're transferring.
Yep.
So how many canisters do you run?
Yeah.
How do you know?
Well, there's a few simple calculations. It depends on the porosity of the reservoir, depends on the volume of rock we're going to cut, it depends on the pressure of the reservoir or the depth of the well. We have a spreadsheet. We work with the client, we work with the lab. We put all the data into the spreadsheet, and it basically gives us, we need to have this much volume to absorb all the gas or liquids that are going to come off the core. So we then take that number and we put a safety factor of 2 on it, and that's how we calculate how many canisters we run.
So what can,
Good
you never
job.
talked much about the valve. What can cause that to leak or fail?
Okay, it's downhole environment. One of the things we have to do is we cut a core, and the core is at the bottom of the bit. The valve is a distance up from the bottom of the bit. So one of the hurdles that we have is we have to actually physically pick the core up and pass it by the valve. This can sometimes cause a problem if the core is, if we have too much filter cake built on the core, we slip over the core instead of actually picking the core up so we can close the valve. That's one potential problem. We can tell you out of over 60 runs, it's happened to us once. Another problem, even though the valve is secured and kept behind steel for the entire time we're coring, there are certain mud systems, there are certain applications, say, be it an unconsolidated reservoir, there could be potential for the valve to sit on debris when it closes, and it could not fully close. Again, we have not seen that. It's just something that we are aware could happen.
All right. Then you spoke to it, but tell me again, what happens if you fill all the volume of the canisters coming out of the hole? If you have enough gas that everything is full?
If everything fills, if our spreadsheet has told us a number and it's a miscalculation, if we're in a sweet spot in the reservoir, the system is designed that when we reach maximum pressures, it leaks. I mean, data is important, but it's not as important as the safety of everybody. And the last thing we can do is bring a tool to surface that's over-pressurized. So we have working limits on the tools. We set pressure relief valves through the barrel and all the canisters. And if we have filled the system full and overfull, it simply bleeds out into the drill string column as we're tripping, or if it's a conventional mode, it bleeds out into the wellbore.
What needs to be discussed there is it's still the pressure relief valve system. So as soon as it drops below that acceptable pressure, it once again closes again. So if it happens during the trip out of the hole, you're not going to lose all of your properties. You're not going to lose all of your liquid and all of your gas. It still maintains that pressure differential between working components. So as temperature starts to decrease, once you come out of the hole and the core starts to go to sleep, it may fall below that threshold and still keep everything contained.
So essentially, you're going to lose the top portion of your information. We're going to be able to see when that happens coming out of the hole, and if it happened 50 meters or 150 feet from the surface, no, we won't be able to quantify the exact amount of gas that's lost, but at least you have this much gas and we've lost the little band at the top for safety reasons.
How often does that happen? You had statistics on the other one. I mean, do you know how often that's happened?
Hasn't happened. No. It would take a lot for it to happen. We would have to core into a really sweet spot. I think where the bigger risk of it to happen is if we're in a pure exploration well where there's no offset data. So right now, typically customers are going back to prove something or to challenge something. They have quite a bit of data on the well already or data on the formation already, so we can do a good calculation. If we were wildcatting or doing an exploration well where we didn't have that type of information, it could be a risk.
It's small because you're losing temperature coming out of the
Right.
hole.
Correct.
So PV equals NRT.
Yep.
It's always dropping.
Correct.
So you gave an example of 3 canisters, and you had a 250 psi. Do you call them crack valves or check valves? Then you had a 50 and a 50. What if you? And then you said you could run up to 7 canisters. How do you determine what the settings are in between the canisters?
Well, the way we do it is, if you remember from the presentation, we have to overcome each one of those pressures as they build. So it's a little bit of a mathematical game where if we say set every canister at 100, you can do math very quickly. If there's 7 canisters, it'd be 700 psi, and the barrel set at 250. We're getting the pressure in the barrel too high. So the pressure relief valves are good to about 25, plus minus 25 psi. So What we would do is if we were going to run several of the canisters, we back down the pressure off the pressure relief valves. So we go 250, then plus 25 is 275, another 25 is 300. We just decrease the amount of pressure between each canister we run.
And then what about tripping speeds? You never spoke about how fast do we, I mean, coring, we're always worried about trip speeds.
Yep.
What about coming out of the hole with quick capture?
Yep. Based on the several runs that we've done so far for different clients, each client, each laboratory has their own types of methods as well. We work with the client themselves, depending on if it's a conventional, depending on if it's a wireline application. One of the recent wireline applications that we did where you think that they would want to trip the barrel to surface as fast as we can, it simply wasn't the case. They spent 12 to 14 hours still slow tripping. The purpose behind the slow trip in this application was to actually try and monitor the pressure and temperature as we moved it out of the hole, seeing how the transducers were acting, how the tool from the barrel itself to each of the pressure steps to the canisters was going. So from our standpoint specifically, we work with the client, we work with the laboratory on the preferred method depending on the formation that we're in. You know, hard or soft, hard rock, soft rock.
There's a worry out there. We take a piece of core, it's going to evolve something out of it, gas or liquid. It's the elusive bubble point. And there's a concern that if we're traveling at 50 meters a minute, that's relatively 75 psi differential drop a minute in a normal mud system. There's a worry that as we're moving that fast that we could actually go right past the sort of exact spot where it starts to evolve, and that by the time our monitors, our pressure transducers and temp transducers pick everything up, we could be quite a distance uphole already that would give a false indication of when those two lines you saw in the graph start to diverge. Some of the clients want to slow the process down so see if they can get a tighter look at when those two lines start to diverge. And it gives them an idea of when the gas and liquids start to evolve out of that rock. So that's why it's incredibly dependent on what the customer wants to see out of the tool. If there's no other questions, thanks for everybody coming today. Glad you gave us your time.